Good afternoon, everyone, and thank you for coming to our WMG group colloquium. Today, it's my pleasure to invite Dr. Chinnapat Panwisawa from Materials Engineering Department at Queen Mary University, London. He just joined Queen Mary University from University of Leicester in July 2022. Chinnapat completed his PhD in Metallurgical and Materials Engineering Department from University of Birmingham in 2013, and he completed his bachelor's in physics from Chulalongkorn University, Thailand in 2008. After confinement of his PhD, he has joined Partnership for Research in Simulation of Manufacturing and Materials PRISM 2 research group in Rolls-Royce University Technology Center at University of Birmingham from 2013 to 2018. In June 2018, he was awarded EPSRC UKRA Innovation Fellowship to conduct his project as principal investigator on additive manufacturability of metallic alloys, where he was senior fellow and EPSRC Innovation Fellow at University of Oxford. Before joining Queen Mary University of London, he was associate professor in digital manufacturing, as well as associate director of NISCO UK Research UKRI Innovation Fellow at School of Engineering, University of Leicester. Over the past 14 years, he has developed predictive capability of additive manufacturing processes, investment casting, laser and electron beam fusion welding of additive manufacturing. So today, Chinnapat is going to give a talk on thermal chemical fluid dynamics of multi-metal additive manufacturing, in-situ alloying, composition control, and species mixing. Thank you, Chinnapat, for your time and giving this talk to our group. And I welcome you to present your talk now.
Thank you very much, Parkas, for a very excellent introduction. I'm very honored to be invited to present to everyone in the metallurgical community today. And today I will talk about additive manufacturing or 3D printing, especially some aspect or some research project in in-situ alloying. So first of all, I would like to acknowledge that the funding body from EPSRC and Royal Academy of Engineering, which actually supporting some research activity in the past years including the result from this presentation. So as you may know, nowadays people talking about metal 3D printing or metal additive manufacturing, or I would call it AM. And one of the most popular techniques they call powder-based fusion, where you have the powder actually spread onto the substrate, and then you use a laser to fuse them together, and then construct it in a specific 3D geometry. There is so many things happen during this kind of manufacturing process, where you need to control and understand what happened in such a very small time and length scale. As you see from this scheme, the laser beam size can be 100 micron in size, in diameter, and then you fuse it in such a very short period of time. It leads to very extreme, physics or cooling that make the microstructure and the property quite different from that traditional made alloys or materials. So the talk today will focus on how can we see or how can we understand the interaction of laser and the matter to basically improve the process for further develop the multi-materials additive manufacturing. And this is something I will focus for today. And as you see from the beginning to the end, from start from the powder and the laser until you get the component level here, there's so many things involved in the process. Which include a physics of the laser interaction with the materials, the chemistry where you want to control whether or not you will get the same chemistry that you use as a powder. So there's some, for example, some vaporization may happen, and then you get some chemistry which is not exactly the same that you want initially. And then material design, definitely process design, in order to actually get the right condition for printed the part successfully. Powder metallurgy to basically get the good quality of powder in order for you to get the quite good quality of the part. And this one is just a fundamental understanding that we need to put together in order to generate some kind of a new approach to accelerate the technology using computational research, which is big data, artificial intelligence, and which I will give you a little bit of how to say progress that we have been doing in this field. So if I give you a little bit of background about the metallurgy in the specific field of the superalloy, I'm sure that some of you may get familiar with superalloy. And traditionally, we use a cast or rod process to basically process this superalloy back in 1940s. But every time we introduce a new process like powder metallurgy or directional solidification or single crystal casting even, we will introduce usually new composition for that. So that is because the reason is because we optimize the material as a function of process that you use. It's probably the same for AM. That's because of challenge at the moment. The state-of-the-art superalloy are generally difficult to print. So many defects can happen. So how can we go about it? There are two aspects. The first aspect is the materials. Second is the process. In terms of materials, so we can use a kind of alloy design computational approach to basically find a way to see what is the available composition. I mean, based on benchmark with a traditional nickel-based superalloy. In this particular paper, we're looking at around 10 million composition. And then we compare or benchmark with traditional alloy and come up with a new processing and also metallurgical window that we hope we can print it better based upon the physics-based model, merit indices for strength, key creep property, and density. And for the process parameter, we're looking at fixing range and strain rate cracking. And this is a first step. We can say that, okay, we want to actually find a new composition benchmark with the traditional available material that we want the property to match with. And then we prove it that with the new superalloy, we can actually print it better. So it's actually defect-free, for example, for a given condition. That's actually published in ACTA 2021. And in addition to that, in addition to the composition itself, we need to think about as well about the process, because at the moment, it's not just fabricating something simple, because additive manufacturing gives you more flexibility to fabricate. For example, you can do laser-based multiple metallic material additive manufacturing. But if you see in the middle of the screen here, the Eiffel Tower, from the bottom, you see copper and the steel on the top. So there's a computationally great printing along the height of this Eiffel Tower. This means that this gives us more flexibility to fabricate something which we can't do before. So the gradient of this is actually has to be controlled in order for us to actually get the property, which may be the new property that may not seen before. So in summary, in this diagram here, normally if you directly join between bulk material A and B, is kind of welding. And the gradient path method here is a way that you can do using only additive manufacturing. And this is, for example, that people try to fabricate stainless steel 304L with the Inconel 625, for example. This can be used for example, repair application. But in order to actually get this technology successfully implemented in the real manufacturing industry, we need to understand a little bit more. So if I try to summarize the challenge in the process design, given that we're looking at three particular methods for 3D printing. which are direct laser deposition, while additive manufacturing. So the thing in common that you will see here is the interaction of the laser and the material, which is very, how to say, extreme at the very short length and time scale. How can we go about it? How can we understand this in order to control subsequent microstructure and the property scatter in the part? So if you look at some of my paper in the past, in 2015, we are looking at something called now powder-based fusion additive manufacturing, or previously called selective laser melting, that if you vary just some process parameter, you can get totally different property in terms of subsurface porosity, for example, here. And that is so important if you want to bring a safety critical component like a turbine. So now we will go inside into the melpool, into the printing technique or printing science or metal physics behind that. So if we zoom in further to see what happened during the interaction of laser and the powder particle here, you will see there's a lot of things going on. It's not as simple as you see in the previous slide. So in this one, you see some particle flying away, and there's some summarize of what is going on here. You see melpool, you have the laser beam interact with this vapor jet domain, which is ejected a particle from this domain. So you can actually divide it physics associated with each phenomenon happen in this process. But in order to summarize all this, I have put in a comment to say that, okay, once the laser interact with the material, you can trigger particle dynamics, which is very important when you have particle flying away. But more interestingly, we want to look at the thermofluid dynamics, or the printing, where the laser interact with the material, what is going on, because it is very important to control this thing in order to get the right solid state transformation, solidification, and subsequent the defect which is formed, which is actually induced during this process. How can we actually understand this few hundred micrometer in order to actually control the whole process? That is the challenge, by understanding the material and the process together. So this is something we call AM by design. So we look at composition and the process together in order to control these two together. So traditionally, when we want to design something, we start from what we want to get out of it in terms of the property. But for AM, we rather need to understand what actually the science or the processing science that actually govern the property or the microstructure which emerge from this kind of process. That is quite actually challenge, because the cooling rate, as I said, the thermal signature in this process is a rapid and repeat cycle, and that make the microstructure very unstable or non-equilibrium state, if you like. And this one has to be understood in order for us to decide further the new component or the new property that you want, in order to match with at least traditional made manufacturing process. So the way we have been doing in the past years is actually using integrated computational material engineering approach in order to answer what is the manufacturability from this process once we understand the interaction of the laser and heat source, and what is importantly key process variable that control everything. So from the particle dynamics in the tens of micro length scale to the thermofluid dynamics in the melpool physics, how it's actually print what is a solidification sequence that we want to know as well from the solidification model, and hierarchical microstructure simulation, precipitation kinetic simulation, for example, to understand the scatter in the process. It's not just everything deterministic now. We have to control the noise from printing process, and then we hope that, I mean, after we understand this micro scale information, we will bring it up, link it up to the macro scale behavior using crystal plasticity or finite element type of approach. Moreover, we really want to actually go further to actually complete the loop of the reduced order model, where you actually take the information or knowledge from the lower length scale information to scale up in the higher or macro length scale analysis, where you can actually retain the property or the defects formation in the lower length scale to that big scale analysis. That is something we envision. So having said that, I want to start to the real context of the talk today. So talking about chemistry process design for AM. So if you know how to say high performance alloys actually is a constituent by the transition metal in the periodic table. If you looking at this, and then the way forward when you want to fabricate multi-materials, additive manufacturing is to mix them together like this, like the technique called in-situ alloying, where you mix these two powder together. This is one way forward that we can do in order to do the compositional grade printing, as I said before. Or moreover, we can actually improve some property using this technique for the current additive manufacturing application. For example, in the biomedical application, when you have a binary system, nickel titanium system, where the nickel actually lost a lot compared with titanium, and then you have to understand how it's happened and how can we compensate the percentage that lost by the process condition. So this is the ultimate goal of working on this. But we want to generalize this into the whole 3D, 4D, 5D transition metal, and then select some material which is available in the aerospace, automotive, and biomedical area. So having said that, we want to extract some chemistry process characteristic actually using the thermochemical fluid flow framework that we propose in this ACTA material paper. And just don't want to go much into the detail of the equation. If you're interested in, could you please go to review some of the equation there. But more interestingly, we see some trend in this transition metal. If you look at the kinematic viscosity versus thermal diffusivity, one of them actually, a thermal diffusivity definitely measure how heat actually spread onto your bed if you use a powder-based fusion process, for example. And kinetic viscosity measure how fluid flow is actually generated. And then if you see that there is some trend in this property when you're looking at the liquid density of this transition metal. And then you see that there is like a manganese actually has higher or likely to flow in a wider region, or I mean more viscosity than gold, for example, which is very heavy metals. But actually gold has larger thermal diffusivity, which is mean that the heat actually spread faster by conduction. That you will see easier when we actually put this one into the simulation, where we're looking at the island titanium, nickel, tungsten, aluminum, and gold. You will see that the characteristic to represent the additive manufacturing process has been captured using chemistry process relationship here. And then you will see that gold, as I said, spread faster by conduction. But again, the fluid flow, which is actually less viscous than manganese or nickel, for example, that generate keyhole compared with some other material like titanium, where porosity only take place, for example. I mean, all these things has been summarized into a diagram we call the elemental AM diagram to understand the characteristic, especially the vaporization or mass loss. So it seems that the heavier elements show larger mass loss. In the group 3D, 4D, 5D, the mass loss normalized by the atomic weight is similar range, but sensitive to the Reynolds number of the melt pool. The Reynolds number definitely, as you know, defined here on the left-hand side, the maximum liquid velocity, the melt pool length scale, is given to be a characteristic length for the Reynolds number calculation here. And then we can see that chemistry dependent on the process, chemistry dependent actually, and then we can extract some trend of the mass loss. For example, heavier elements, larger mass loss. For example, the trend is actually has a relationship with the flow, which we can't use traditional FE simulation to extract it if we're not considering a fluid flow, for example. So, and the trend in the diffusivity is not very much clear, and that's why, I mean, why there's something called platelet number here. And this one, I have to know that this is at the representative condition that we use to apply for the whole range of the material, which is, as we all know, that it has to be optimized for a particular material system. But this kind of study give us some guidance. How can we actually fine tuning some material system to get better processability? Is a first way to do that. So once we understand the elemental behavior, we want to mix them together now. The challenge is actually is quite high because we have a lot of things we don't know. For example, interaction term, interfacial energy. But we want to use some kind of traditional rule of mixture type of assumption to go further to get to the in-situ alloying of these two materials. For example, in this system, we have nickel titanium alloy, where you can quantify the vapor mass or mass loss from a pit as a function of a process parameter. And this one, we can quantify the vapor, how to say, mass as well. And this is actually a very important step for us to understand how things mix together. That's why in the title called species mixing. So this is a concept, and then once we do it, implement this in a multi-layer part-based simulation, you will see that now we don't have only a single material. We have nickel 50%, titanium 50% spread onto the bed, and then we can actually see how things mix together. And I mean, if you choose the wrong parameter, you will see very clearly that the mixing is not very good, and that is why defects actually emerge or form. And then you see after second deposition is also at this process condition, it seems to be that, I mean, the mixing is quite good. But the question after this is that how can we actually use this information further to the microstructure development and the property prediction as well. So give you some example that at the moment we use in the in-situ alloying or mix them together under the beam, actually for a new metal glass composite for better implant. As you know, traditionally, and we all use now, is a titanium 64, a medical grade. It's used for biomedical devices. And we have a project under the support of Royal Academy of Engineering to explore another territory in terms of the material process system, where we can actually improve this better. So we are looking at a partnership with Thailand, looking at titanium copper zirconium system, where we want to get the processing and the chemistry right to achieve the perfect implant at the end of the day. So just give you a bit of flavor what actually we can do. So we have to meticulously control chemistry and process. And this one we have to representative process condition that you will see from the chemistry map as a result of this high fidelity model, that there's some different if you vary the process condition. And this one can be quantified and predicted if we use this model. And also not only that, we can link further to the solid state transformation. If we get this right, that your thermal signature will be right. And not only that, the trend after this is actually chemical signature. We need to get it right as well for additive manufacturing. And there is another process that I mentioned earlier, which is not part of it now. It is direct metal deposition, where you want to deposit different material on each other. For example, this one is kind of alternate titanium and a refractory metal deposition, where you have titanium niobium, for example, or titanium molybdenum pair. And our study here is to understand how the species actually mix together, and what is the barrier when you want to actually use this direct energy deposition to repair some component. Why it doesn't work from thermal chemical fluid point of view? We can have some explanation on that. That's because of, for example, we are looking at the same map, viscosity versus diffusivity, but we now focus on the refractory metal. We can see from the next slide that there's some trend that some heavy liquid density doesn't mix very well at this process condition. You will see tungsten make it nearly a laminated structure compared with titanium niobium or titanium zirconium. And this is why some of the application using tungsten additives doesn't mix very well. But anyway, we can use this kind of simulation to explore even further. How can we improve this mixing? So I'm now going to the next part of the talk. When you have or mixing or thermal fluid characteristic, you want to link this one to the grain structure prediction. So I mean, simplistically, the thing you will do first is to take the thermal field from the simulation at the lower length scale, and then you actually scale this up to the domain investigated, and this will follow, the grain will follow the solidification front or thermal gradient, for example. But in reality, this kind of simulation can be kind of statistical mechanics-based simulation, like Monte Carlo or Monte Carlo type simulation. Whereas if you want to impose more physical phenomenon into it, we may need to use a kind of modified phase field or kind of stellar automata type approach that we will mention a bit later now. So in order to actually understand the role again, not just a thermochemical fluid, but also link this one to the solute field, which actually happen in the solid state of the material. We actually now investigating the role of the interaction of the laser and the powder as a function of the chemistry, and then we can elucidate some phenomenon like solute trapping or rapid solidification that leads to non-equilibrium microstructure, which this work is quite important, because in order to understand how materials solidify, it's important for microstructure and property scatter in the process. And for example, if we use an in-situ alloying, how can we understand what is this solidification pathway for that system? And that's what we are developing a mathematical framework to do that. Having said that, our things going to do next is actually with regards to the precipitation model. I mean, as you know, there's some concern that the phase which is actually present into the printing is not as anticipated, because once you want to fabricate nickel-based superalloy high volume fraction, nickel-based high volume fraction gamma prime nickel-based superalloy, but you hardly see the gamma prime at the as fabricated state. That is because of a non-equilibrium nature. And once you do some post-treatment, this will start coming up. And then how can we understand and then maximize the use of the model in order to give some direction for the post-treatment? This work, put a shade and light onto that. So we take a thermal history from the lower length scale information to predict the precipitation kinetics, and then we will see that there is some in as fabricated condition. So the precipitation, how to say, wavelength can be observed here. So there is some large gamma prime, for example. This material is Inconel 718. If you want, you can follow our paper back in 2018. This is 4 or 5 years ago now. So we can actually understand why and how the build here is actually distorted and why the residual stress are developed once we actually link this kind of result to the mechanical analysis. So the ultimate goal, as I said, is to, for example, if we use a nickel-based superalloy as a model, we can say that we want a property of high strength, high ductility material like CM247. That is a community want to match the property or the behavior to be like that. But the problem is that doesn't actually work very well in the current printing condition. How can we improve that? I mean, we use actually computer simulation to understand as well from the printing until the post-treatment in order to, justify or rationalize that why it doesn't work, and then how can we improve it? That is the next step we are working on. So in the paper back in 2021, we have published in Additive Manufacturing to say about the manufacturability of superalloy. We took 100 superalloy composition and also estimate or calculate the property of that, and then benchmark with the Inconel 718, which is the very well-known alloy which has a lot of fluid property measured. So we benchmark on that, and then we generate the kind of, it's called thermal fluid map to say something about manufacturability using porosity, cooling rate in the liquid state. As is shown here, from the liquid to solid, and then because there is some different cooling rate, as you may notice in your measurement, if you do some in-situ thermal imaging, thermal monitoring, you will see that this actually happened. And more importantly, from the kind of high fidelity model, we can generate something called a mass loss map as well for superalloy. And then you will see from this, nearly about 35 calculation here and map in a contour that the newly developed composition for additive manufacturing actually sit in the good printability region, where you have less porosity, less mass loss, and also cooling rate is not very extreme compared with some high gamma prime former superalloy. And this is because if we understand this interaction and then we summarize map for superalloy here, you will see that there's some hotspot from the thermal fluid point of view that you can get some kind of processing window that you a lot of mass loss or get a quite optimum cooling rate. And I have to note that this is at a condition investigated. So we need to use this information to actually optimize further for a particular material and process, also machine as well for additive manufacturing. And last but not least is actually how can we actually make use of all the lower length scale information to the larger length scale analysis. So if we are looking at some material system like Thai 64 or Inconel 625 here, And a normal thermal simulation available now hasn't been taking into account much the lower length scale information. But now we want to actually develop something called reduced order model that take information from the lower length scale into account in order to get the thermal signature right, and as well later chemical signature right as well. So like this one give you some example like Ti-6 for with and without evaporation. You will see that the melt pool actually predicted is actually rather different. And once you're building up in height as well, you won't be able to get a steady state melt pool by the way. And this is why we want to develop this kind of model, but it's still not very cheap computationally anyway, but it's actually cheaper than this high fidelity model, can give you some kind of predictive capability for further upscaling or further digital twin type of model. So this can quantify that model, capture some physics of prediction that you may anticipate it from experiment. And this one, I mean, we explore as well the territory of the multi-track, multi-layer deposition, where we actually have fabricated, I mean, in this slide, 5 layers. And then you will see that the melt pool actually develop further and further. There's no steady state melt pool anymore in this process if you not actually choose this right window to do so. I mean, that's why if you understand this kind of physics or underlying mechanism, we can actually optimize the process better for a while. I mean, currently available material like Intel Xenon A625316 and aluminum alloy. Yeah. So having said that, our vision is actually to develop toward a digital twin for this for hybrid manufacturing to link up the micro scale information defects to the macro scale analysis using this reduced order modeling approach. And then we hope that this comprehensive data from the lower length scale information can be further developed using for machine learning based model for digital twin of different or multiple material manufacturing. And this one is a work in progress to include all the defects formation as well in the process. That is something we want to do. And having said that, I want to summarize the talk today. The computational fluid dynamics or CFD can be used to study liquid metal behavior, particularly in a printing condition for additive manufacturing. And this understanding of the solid liquid vapor transition is a key to capture thermal and chemical signature, defect formation, resulting microstructure, and scatter in the property. Prediction of this microstructure variation induced by this localized liquid-solid reaction can facilitate a process design for further develop for a particular material and process system. And better understanding this scatter, as I said, a lot of things in additive is stochastic. It's actually everything, yeah. So we have, how can we understand this actually noise or statistic of the process and use for material design purpose, especially for a new material for additive manufacturing. And then we hope that this fundamental understanding can be used as a knowledge for the AI-based model to simulate physical effects in AM by linking this material process information, establishing a digital material design for next generation metal additive manufacturing. Thank you.
Thank you, Chinnapat, for wonderful talk. And any questions from audience?
Thank you very much for the talk. Very interesting. Can I just you have to excuse me if I missed what you were saying earlier, but did I understand correctly that you were saying that in terms of elemental losses, that the elemental losses are linked into the atomic number of the material or the elements that you're trying to alloy when you're doing the in-situ alloying?
Yeah, I mean, elemental loss characteristic, we extract from the elemental processing. So it's just individual element by using a single or identical process condition to extract that. And there is some trend we need to explore further, actually, whether this is because this is all computational experiment. There's no real measurement, but we have put some kind of effort to look at the to go further to the chemical imaging, because we all know that in type 6.4 there's some loss of some particular element for sure, and there's some condensation that is quite challenging from the modeling point of view as well to simulate that. And then I think this is kind of first attempt. How can we go about this elemental loss to quantify, to simulate it, and that in a systematic way? And that's some subsequent work that we are working with some other people, which may coming out hopefully later this year or early next year. So we can, yeah, definitely it's linked to that, but we are confirming that. Yeah.
So okay, so you've sort of got some evidence from the computational modelling that indicates there should be a link with atomic number.
Yes.
I was just wondering, because all I know about is steels, I was wondering if this kind of approach would translate into steels where we probably have, well, it's more complicated in terms of the number of alloying elements that are present.
Yeah.
Perhaps slightly greater range of atomic number, but you know, I guess in principle the physics should be the same. So I was just wondering if you could comment whether you think your the indications would translate into steels, and also if you could just explain to me why there is that link between the atomic number to the losses that you're seeing.
Yeah. Just to be honest with you, I haven't had any project working on steel for in particular. But I mean, most of my work is on nickel or titanium or some other metal glass kind of system. But if I mean, definitely I need to run some simulation first to say about the steel in terms of mass loss characteristic. But the thing I can say from the work that we have been doing, there is some trend actually for steel, and then the alloying element that have some potential that is maybe some loss. But as I said, this one is just a basis of fundamental. I mean, it's a component for that elemental loss. We have to investigate in a particular material system that you are interested in. So and this one you are talking about alloyed powder, right? It's not in-situ powder. So it's something that was a little bit challenging as well from computational point of view. But anyway, we prefer in-situ alloy. But I'm sure that if we understand better the material that you are talking about, I can comment more on that. Yeah.
Okay. All right. Thank you very much.
Just don't have chance to look at the steel, because this one, as you see, I'm not just a simulation guy. I try to link simulation and metallurgy. So this is a big challenge, and then that's why it's have to. Yeah, I can't comment much if I don't study that well. Yeah. Thank you.
Okay. No, that's fine. Thank you. Thank you very much.
Thank you.
Thank you. Yeah, I think a couple of questions. First, Michael.
Thank you, Prakash. I hope you can see me now.
Yeah,
Sorry.
yeah.
Hi.
Thank you very much for the very impressive talk. I guess my question relates a little bit on the loss part of it, but more generally speaking, you are observing a lot of effects that are more or less random, like droplet formation, the bridge shape in the liquid melt pool. I'm just wondering how you're trying to capture this. Is this something where you relate to statistical data from experiments, or are you actually trying with Monte Carlo methods from physics-based simulations in order to tackle that kind of randomness?
Yeah, this is very good question. I mean, I would like to answer in this way. I mean, two parts. The first part is actually we actually curious about what happened in the physics of this non-equilibrium state. And then we had some collaboration actually with experimental people, let's say from UCL Imperial, to investigate more. I mean, they so interested in vapour. So that is perfect with how can we actually rationalize something actually happen in the process, so as a function of materials or composition. That is one question. The second question, second part of this answer is that how can we link this one to the statistical based approach to do that? This is some, to be honest, this can be a proposal big project, because I mean that's what we are trying to do as well. I understand that we have so many experimental data, but it's not actually correct in a more in such a way that we can use for a big data analysis. So that's why our idea is to basically we can't do thousands of conditions, right? The maximum we can do tens of conditions, but we have to use this simulation to guide or what is the window for that, and then we can prove in a particular condition. That is exactly the same that we've been doing at the moment for some in-situ alloy system. As I mentioned before, there's some confirmation that the loss is actually there. It's real phenomenon. The mixing is actually very, very real. I can say from PMA result that we have investigated in some, because it hasn't been published yet, so I can't say much. I mean, that is so real. And then there's some loss, especially some paper that we published in NITI. The loss can be up to 2 atomic % in nitinol material, which actually make the transformation temperature shift significantly. We can't bear with that. We need to compensate somehow. I mean, that is the implementation of the code. How can we use this information for the statistical approach to actually further develop this? I think, to be honest, has to work with people now. So because I mean, we can't solve everything. I have to be honest with you, and then that's why we are now trying to. If this is something you are looking at, so we can discuss further. Yeah, thank you very much.
I wanted to mention that actually, if you're really interested in this, we are actually working on this in a different aspect. We are identifying the most sensitive parameters based on random events on failure.
Yeah.
But the theories are applicable. Hence my question. Yeah. So if you want, I can send you a separate email on this.
Yes, please. Yes, please. If you have my email address, I can drop in the chat box if you want. Yeah.
Thank you.
So, thank you very much. Thank you.
Thank you, Michael. Carl?
Hi, I'll just be on the other screen. Thank you for that nice talk. Really enjoyed it.
Thank you very much.
A lot of the alloys that the additive manufacturing industry has been working on are alloys that have existed for a while and have been produced by conventional production routes. So you got 316 and Ti64. And I think, I guess my question is how far away do you think we are for designing alloys? For a lot of these alloys have got additions in there to make it easier to cast or easier to roll or easier to forge for the nickel alloys. We're directly turning those alloys into powders where they don't need to be forged or don't need to be, the casting is different. How close can you, or how much do techniques like this helping design for AM rather than just using current alloys, and how easy would it be to get those into the market? I know you mentioned that automotive is one of the applications, and they very much stick to standards. They love standards for everything, and so how easy? And how easy do you think you'll be? How easy do you think?
I mean, let me try to repeat your answer, your question. It's actually you're asking how can we use the traditional legacy or existing alloy or for additive successfully, right?
Well, not quite. Is it possible to throw out the rules of current alloy? If we want to make a 316 type material,
Okay.
some of those additions are made to make it easier to cast and process.
Of course, yeah.
Yeah, can we throw the rule book out
and we
and
live
start
with existing alloy?
Yeah,
that's what you said.
Yeah, and what are the barriers of getting those to the market? Is there going to be a standards for AM alloys because they're going to be different?
This is very extremely good question, actually. So I mean, behind the I just say the way behind the idea of the presentation, we believe that AM will change how we make things. That's his first thing, as you said, from in-situ alloy or whatever. But as you mentioned, or as industrial people may want, is actually how can we live with the existing alloy? And the thing is that if you ask me, I would say that we need to understand the fundamental characteristic, like what we are doing, in order to actually adjust the composition, because I believe that the chemistry and process is actually linked to each other. Normally, traditionally, you are living with some simple thermal cycle, like casting, heating up, hold it, cool it down. Forging is pretty much the same. And when you go to the very severe situation like additive, not even welding, because welding you have only one cycle. But this one is actually cause some challenge which we don't know yet. So that's why if you have some loss, for example, if you know there's some loss in this manufacturing process, and then we try to actually get away with it, compensate some composition, the traditional or existing alloy may work, but I mean, given that we don't have much, I may be wrong. Computational study to understand or rationalize what happened in the real manufacturing condition, which actually I have to accept to you as well. So all of my publication is driven by curiosity. So we need to link with industry to actually, maximize the use of the model, and that is one way. Even I get some support initially from Rose, back in 2018 on this fellowship. Yeah, that is my answer. I think if we understand fully, we can say that okay, we can't live with it, or we can live with it by adjusting some composition, which considering of processing route as well. And that is something not just for my personal thought, not just only thermodynamic calculation, in my opinion. Yeah. Thank you.
Brilliant. Thank you very much.
Thank you. Any other questions? If not, Chinnapat, as far as I know, like in 3D printing, most of the metallic alloys, the structure, microstructure is the problem, right? Like columnar grain structure, and they're trying to make it like more equiaxed structure after 3D printing. So anything in those kind of like your suggestions, like what are the aspects going in that microstructural development to transform columnar to equiaxed?
Yes, that is very good question, actually. So I mean, this is actually the trend at the moment for modeling people to do as well. Try to go to the microstructure development, considering all complication in the process. And the first attempt that people working on, I'm talking about simulation community, is actually use a statistical approach where you're not taking much physics into account. So I mean that the new way of doing that now is to link all the physics. What it will make complicated thing, but in order to extract some characteristic, like the grain growth characteristic. As I said, everything has to scale up. We can't run a simulation of 100 micron, 100 millimeter even. As in this thing. So at the moment, people trying to do that. evident by some paper from NUS, for example, from USA. Yeah, and then we are trying to, yeah, and I give a bit of flavor what we are doing to understand the solidification pathway.
Okay.
Before we actually say about whether equinox or columnar, that is a bit larger length scale, if you want. And then once we develop that fundamental understanding, we will, I mean, confidently links up to the bigger grain model that can tell you about that. I mean, if you are fabricating some biomedical devices, the width of 100 micron, this is so matter, the microstructure. But if you are talking about automotive part, I'm sure it's definitely bigger. So it's as I mean the point I want to make that is about the application as well. You are talking. If you are talking about some application of the cross section, few millimeter, so this kind of high validity model will be very useful. And yeah, and for, let's say, for steel or heavy industry part of application, I need to understand more. I know you are working on steel, right? And then yeah, so thank you very much for your question.
Okay, thank you. Any further questions from audience? Okay, if no more questions, I once again thank you, Chinnapat, from our group for this wonderful talk. Okay, and yeah, I wish you all a very good afternoon and thank you.
Thank you very much indeed. Thank you very much. Thanks for invitation as well. Thank you.